Nearly 3,000 years ago, the ancient Greeks imagined Talos, a towering bronze guardian designed to protect the island of Crete. It is the earliest recorded instance of humanity dreaming up an autonomous, artificial being to handle human labor. For centuries, inventors tried to bring that myth into reality through mechanical imitation. Creators like Jacques Vaucanson built incredibly intricate clockwork bodies that could mimic biological movements, like playing the flute or eating, but they were completely devoid of reasoning brains. In 1950, British mathematician Alan Turing proposed a different approach. He argued that we should stop trying to build a physical body and instead see if a machine could execute formal, logical reasoning. 8 years later, engineer Frank Rosenblatt built the Mark I perceptron. The perceptron was the very first mathematical cell, an artificial neural network capable of learning how to make simple binary choices based on data rather than strict mechanical gears. That mass of physical wires laid the foundation for modern artificial intelligence. It shifted the human pursuit away from mimicking physical form, focusing entirely on the replication of logic. For the next several decades, computer scientists scaled that single digital cell into vastly more complex systems. The 1980s brought specialized expert systems, and by 1997, IBM's Deep Blue was defeating world chess champions through sheer computational search power. By late 2022 and 2023, the industry experienced a massive explosion of large language models, or LLMs. An LLM is an artificial intelligence system trained on vast amounts of text data to understand and generate human language. They became enormous, hyper-intelligent digital brains holding the sum of recorded human knowledge. This animated diagram illustrates the core flaw of that era. Despite its vast knowledge, the AI was fundamentally a brain in a jar. It sat perfectly still, completely dormant in the dark, until a human typed a prompt and sparked it to life. Because the architecture was strictly generative, it could only predict the next word in a sequence and then stop. It couldn't browse the web, it couldn't trigger a software tool, and it had zero memory of yesterday's conversation. It was paralyzed. We had built an oracle that knew almost everything, but could do absolutely nothing on its own. To be truly useful in the real world, the machine needed the ability to initiate actions without human intervention. In 2024, developers broke the AI out of the chatbox by giving these language models access to external tools and persistent memory. This created Agentic AI. Instead of just answering questions, an agent can operate independently using a framework called the REACT pattern. REACT stands for Reason and Act, a method where the AI cycles through thinking about a problem and then taking concrete steps to solve it. This flowchart illustrates System 2 reasoning. Complex problems are broken into logical steps. Given a broad goal, the agent automatically searches the internet and queries databases. If it hits a dead end, it evaluates the failure, rewrites its code, and tries a different route. The software evolved from a calculator that responds to queries into a digital worker that actively solves complex problems. By March 2026, the industry standardized around massive frontier models, engineered specifically for deep continuous reasoning. Models like GPT 5.4 handled massive enterprise planning workflows, while Claude 4.6 could sustain focus on a single coding task for over 30 hours straight. At the same time, models like DeepSeek 3.2 drove the cost of inference down to fractions of a penny. Inference is the computational process a model uses to generate its output. With cost plummeting, running an AI agent continuously in the background became economically viable. This triggered the patience revolution. The metric of success was no longer how fast a model could instantly spit out text. The new standard was whether the system could work quietly for 3 days without hallucinating or losing its context. We stopped measuring raw computing speed and started measuring the reliability of an always-on cognitive workforce. By early 2026, over half of all enterprises had already deployed multi-agent systems directly into their live production environments. Here, specialized agents for research, coding, and review communicate directly to finish workflows. The human role moves up. You no longer micromanage tasks. You sit at the top of the hierarchy, orchestrating these autonomous digital teams. The modern enterprise became a hybrid society, where human directors sketch out the vision and digital coworkers build the reality. The final leap was physical AI. Engineers took these reasoning, agentic brains and placed them inside advanced robotic bodies. They achieved this using vision language action, or VLA models. A VLA model allows a robot to process visual data, understand spoken human commands, and autonomously map out the physical actions required to navigate an unstructured environment. 3,000 years after the Greeks told the myth of Talos, we successfully built the autonomous entities our ancestors dreamed of. The human-computer relationship has completely inverted. We no longer ask a machine, "What should I do?" We instruct it to "do this for me." A quiet panic has spread through the technology sector. Some of the top labs are warning that the rapid growth seen over the last few years is reaching a hard limit. This limit is known as the data wall. Large language models require massive amounts of text to grow smarter, but we are running out of high-quality human writing. The internet has been scraped nearly clean, leaving these models without the fresh data they need to improve. Prominent researchers have signaled that the foundational era of pre-training, the phase where an AI learns by simply scanning existing human knowledge, is finished. This feels like a crisis because of how we have used technology for decades. Traditionally, the computer was an office automation tool, a high-powered filing cabinet. You created a file, the machine stored it, and when called upon, the system would retrieve that exact human-made data. The panic of the data wall only makes sense if you assume computers will always be filing cabinets for human history. But that model of computing is currently being replaced. NVIDIA CEO Jensen Huang defines the modern data center as a generative factory. Its primary function is the mass production of intelligence as a raw material. This illustrates the difference. On the left, old computing. A search query pulls a static file. On the right, the new factory. A cluster of GPUs synthesizing a brand new intelligence token from scratch. A token is a basic unit of data, like a piece of a word, generated in the moment to fit a specific context. These factories do not look backward at files. They process current information and generate contextually aware responses in real time. This shifts our path toward artificial general intelligence, or AGI, a system capable of matching human intellectual performance. AGI is no longer a search for a single software breakthrough. It is a task of industrial scaling. Achieving a digital worker capable of running a business requires us to stop mining human data and start scaling computation across 4 distinct laws. The first law is pre-training. This is how current models learned basic language, by memorizing the patterns and grammar found in the mountains of human data already on the internet. To move beyond human limits, we use the second law, post-training. Here, the AI uses synthetic data, information generated by another AI, to refine its own reasoning and logic. The system takes a single seed of human-verified ground truth, augments it, and blooms into millions of new, highly accurate training examples. By teaching itself through this closed-loop system, the AI makes the data wall irrelevant. It can create exactly the training data it needs to improve its own performance. Grounded. Since the data supply is now effectively infinite, the constraint on AGI shifts. The only remaining barrier is the amount of hardware and energy available to process this self-generated intelligence. The third law is test time scaling. This is the stage where the AI stops reading a prompt and begins thinking about the solution. Thinking is compute heavy. It requires the AI to pause, plan a strategy, and decompose a complex problem into smaller, manageable parts before providing an answer. Instead of guessing the next word, the AI builds this, a complex logic tree. It explores thousands of potential reasoning paths in parallel, verifying each step and pruning dead ends until it finds the most logical solution. Previous chatbots relied on simple pattern matching to provide instant responses, lacking the capacity for this kind of internal planning or verifiable logic. This active reasoning phase is the most resource-heavy part of the journey. It turns the generative factory into a thinking engine, where more computation directly equals deeper intelligence. The final leap is the fourth law, Agentic scaling. This is an AI that can spawn specialized sub-agents to manage complex teams and use digital tools autonomously. Huang describes this as the iPhone of tokens. Applications like OpenClaw have turned these reasoning engines into accessible tools that any consumer can use to deploy a digital workforce. Running these teams requires extreme co-design. Every layer, from the chips and high-bandwidth memory to the cooling systems, must be built to function as a single massive computer. The physical requirements are immense. A single server rack now contains 1.3 million individual components, all working together to process intelligence at the scale of an industrial plant. AGI is an industrial achievement. It is the result of 1.3 million physical parts working in perfect synchronization at the speed of light. To build a digital system that can start, grow, and manage a billion-dollar company, you have to look past the simple ability to answer questions. You need a system that can coordinate complex organizational tasks over long periods. The 4 scaling laws provide the mechanics for this AI CEO. By combining deep internal reasoning with the ability to spawn sub-agents, The system can autonomously conduct market research, manage global financial risk, and direct the software development needed to scale a business. Our bottleneck is no longer a lack of human knowledge. It is simply the physical speed at which we can construct the factories needed to power these systems. As these factories proliferate, the global economy will shift. High-level intelligence will move from a scarce human resource to a mass-produced industrial commodity. AGI will not arrive as a singular miracle. It will emerge from the constant hum of planetary-scale factories, bound by nothing but the laws of physics.